Yeah, just kept doing the while loop. Yeah.
We're wondering why our batteries went down so quickly.
Yeah. It took me a while to figure out that was just running like forever.
Oh, wait. How did you create your source code file?
What do you mean?
Did you create it using like WordPad, text edit?
No, I did it via.
I used Text Wrangler.
I mean that in the biblical sense.
Wrangler?
That's what I did.
Who else had problems with the code working?
But I checked the video, and in the example code you gave, the class actually never terminated either.
Yeah,
that's
it's just,
what we're
it
talking
doesn't throw an IO exception when it gets to the end of the file like that, so it never throws.
I got you. So it looked like it terminated, but it didn't terminate.
Yeah.
I got it.
It's like,
So you're telling me that
Kickoff was happening.
all of a sudden, like, I'm only using one application.
I know.
It shouldn't be doing this.
It's been running
all day. It's like fire shooting.
all right, shut up. All right, so here's my source reader. There's get token. Here's read tokens. So we're doing this as long as cur token is not null. So this is an infinite loop, you're telling me?
Yes. Yeah.
That it can't be true.
No, it's in the.
Oh no, that one is the infinite loop.
Yeah, but
Yeah, it never gets to null.
It never
Yeah.
gets to null. It's never going back to null.
right, but it would keep printing out line after line after line.
It's printing out empty space. It's just
But it's doing a println.
yeah.
It should kick it down a line.
Well, that's true. That's true.
I should see this flying off. I mean, I see this. I see that that's. So what must be stuck?
That's a good point. Though.
What must be stuck is it must be in the last run through get token.
That's what we're.
This has to be where it's breaking. Because if it wasn't here, we would see space. We'd see the scrolling off.
Okay, so what it is the last the end of file character or whatever it is. It's not.
It is stuck in the loop. It's just not. It just never gets like a return value big.
Right. The loop is inside get token.
Yeah.
Not the infinite loop is inside get token, not in read token. Okay, so that means that. So while it is white space, this preleads it. Then we read in. So we get our very first character. Then while it's not white space. And val not equal to 10, I think is what was 10 the end of file?
No, -1. 10, I think is. I don't remember.
10 was the enter, a return.
Yeah, return character.
I swear it was. There you go. That's a big. Hey.
Okay, so that breaks us out of it.
He's plugged in.
Oh.
All right, so the token, so that breaks us out.
No, it's just I don't wear pants.
What? Second.
Yeah, like people, they look at me and fill pants in their own pants.
Does read return -1 every time the file's over, or just like when it hits the other file?
When it hits end of file.
Well, because
So
you
here-
skip leading white space part.
No, what I'll do right here is I'll just say if val is equal to -1, return null.
Because otherwise you have the skip leading white space part that would like do a read, get -1, but
There.
it would try and skip white spaces.
All right, so the very last time we finally printed out a null because that was the end of the file. So as we're reading those tokens. So the problem was we weren't accurately seeing the end of the file. So I purposely put that in there for your debugging pleasure.
I'm sure you did not gain any pleasure in that.
I win.
It was an easy fix.
I caught it.
I got to figure out what's going on. It's kind of messed up.
What's up?
Nothing.
What did you say was messed up?
No, it's okay. Moment's gone.
Okay, so anyways, so the only thing it's doing right now is the very last time through, we finally get a null. That lets the null string lets us know that we're done. Okay, so our very last token we need to ignore as we're creating our lexical analyzer. Okay, so for the homework, you were to produce this, right? Something in that format. So for each token, we need to lexically analyze that token. Make sense? Okay, so we're going to create a function. Okay, I'm going to make it public for well, yeah, whatever. I'll make it public for right now, and then I'm lying. I'm going to make it private for right now. Then I'll loosen it up if I need to. So private string lexically analyze. Is that spelled right? Okay, so this function is going to take in a single string that is a token, and it's going to analyze it and spit back out an answer. All right, so again, let's look back at our documentation here. If I read in something like this, like position, and I send that into the lexical analyzer, what I should get spit back out is this token. Just this guy right here. Yep. You see my mouse moving?
Yeah.
What was confusing?
At first it's like it just meant ID.
No, this whole thing.
Yeah.
This guy.
I'm feeling it.
Okay, so I'm taking the token position. Shut up! Okay, I'm taking the token position, and upon lexically analyzing it, I should produce this guy right here. Okay, so I need to determine that guy is an identifier. How do I know it's an identifier? It's an identifier because it's not a operator, and it's not a something that starts with a number. Tokens would never be white space, right? Because this is assuming we've read in that token. Okay, so we currently have a thing called reserved words, right? I filled up with our, so we're going to create a couple of private functions in here. One's going to be called private is, well, here, for right now, let's just say everything is a reserved word. You know, all those operators are reserved words. So I'm going to say is reserved word is the,
Holy cow, look at copying my code.
all right, so, and this guy's going to be a Boolean. I did teach you how to program.
Oh yeah. Looks like I'm copying your
There is actually truth to that. When I go back and I see former students who are now actually became programmers, you know, so not like you people, but their codes, their coding style is similar to my coding style. So it's like my way of like my legacy living on. It's my progeny.
Wow.
All right, so is reserved words going to take in a string token, and it's going to return true if it's one of these guys inside of our reserved words array, and false otherwise. Okay, so I'm going to say for int I is equal to 0. Actually, I'm not even going to do that. We're going to do a for each loop. So we're going to say for string RW in reserved words if RW dot equals token, return true. Return false. So this will spin through all the reserved words, and if any of those guys match our token, say yes, this dude's a reserved word. If we survive that minefield, exit the for loop, checking all the reserved words, will return false. Guy was not found. Make sense? So this function checks to see if something's a reserved word. So inside of lexically analyze, the first thing I can ask is I can say, if this dot is reserved word token, if that's a true statement, what do I do? Well, let's look in here. What do I do to reserve words? So when I see the equal sign here, that guy's a reserved word, right? What do I produce from reserved words? The reserved word inside of the angle brackets, right? Okay. So what am I going to do? I'm going to return the string less than concatenated with token concatenated with the string greater than. That's what I do for reserved words. Make sense? Okay. If it's not a reserved word, it might be a numerical constant. Okay? So I'm going to write a function for this, even though it's going to be a pretty stupid function, because we're probably going to enhance it later on when we start having other kinds of constants. So I'm going to say private Boolean is literal. In programming languages, something that is a hard-coded value is called a literal. So is literal is going to take in a token, and right now, the only kind of literal that we have is a numerical literal. That is, if token's first character is a number. So we'll return whether or not token.char@0 is a digit, using the characters class isDigit method, which is the same thing as just checking to see if it's either a 0, a 1, a 2, a 3, or 5, a 6, a 7, 8, 9. I might have skipped something there, but you get what I'm saying. I'm upset. I shot an 81 in the simulator today. Finished with a birdie, too. Garbage, an 81. So I guess the good news is I had my second yoga class last night, so I was able to actually swing a club today. Possibly. Yeah, there was a 5 or 6 second period there where I totally went Mr. Miyagi. It's the balancing portion. The yoga class is broken into fourths, quarters. So the first part you're like, it's dynamic stretching crap or something, like warm up. Then you go to power yoga. That part is insane. I don't know how people do some of those things. You're in this position and it's like, okay, now just walk to the front of your mat. You're like supporting your entire body weight in like the splits. Then she just casually says, walk to the front of your mat. Stand up, breathe. I'm like crawling to the front of my mat on my knees. I'm not walking to the front of my mat. I'm like getting up like a fat guy. It's like, oh, it's like, breathe. I don't know how she keeps a straight face. But then we do this balancing portion. The balancing thing, is you start off, you're standing there and you're supposed to, here, I'll show you. You're supposed to do, you're supposed to, balance like this initially. Like that. Oh, look at this. Miyagi.
About to do the crane kick.
Oh man, this is better than I've ever done in class. We're just gonna keep going.
This could be pretty good.
So, anyways, but I have to cheat and I have to do the kickstand like this. So you have to hold yourself up at first with the kickstand, and then you slowly get your foot off the ground. Somewhere in here is when I went Miyagi. Then you gotta balance out here like this. Yeah, I'm way better in here than it must be, because by the time we get to this balancing thing, my quads are just blown out because I've been supporting 350 pounds of body mass on one leg. Huh? I don't wear any pants. She said barefoot, so I just decided to take that to the next level. I try to be an overachiever. So- It's like, and it's like the ultimate country club experience too, because like right outside my logo, like I walk out the door from the yoga class, and right outside there on Tuesday nights is the all-you-can-eat pasta bar. So I put my order in, and then go downstairs and put my yoga mat back in my locker. Then I come up and I have to replace all my calories. You know what I'm saying, Dane? And the pile of slop they made me last night. I told them just have fun with it. It was like a 5-pound bowl of pasta. Everything was nuts and bolts and mushrooms and meatballs and shrimp and bacon and
Sounds good.
there was all sorts of stuff in there. All right, shut up.
Can't help it.
Only I get off topic. Okay, so is literal for right now just returns whether or not the thing starts with a number. Okay, so if it's a reserved word, do this. Else if this dot is literal, passing it the token,
Could we possibly do just an or up there?
we could. We're going to return. The reason I'm separating them for now is because we might actually do something different with literals than we do with reserved words later. So I'm just trying to keep it as kind of, I don't know, fluid as possible. All right, so we do the exact same thing for literals as we did for else. So, if we're not looking at a reserved word and we're not looking at a literal, what must we be looking at? An identifier. Okay, must be looking at an identifier. Now, if we're looking at an identifier, what do we do with it? We got to do a couple things.
Put it in the brain.
Okay, so we have to have our symbol list, right? We have to have our list of symbols. So I'm going to create a new object. Now, interesting question. How many of you created an object for your list of symbols?
I just used an array.
I just use a string array. Why is that?
I just didn't array this.
No, there's nothing wrong with it.
Well, that's what I did.
I'm just seeing how many of you did this correctly.
You said we could just use an array.
I did. No, I'm not going to mark off points. I'm just looking at
points when it comes to teacher evaluation time.
like anybody looks at that.
He was like, do this, and then when I did that, he's like, oh, you did it wrong. It's a dick move, man.
Also, there's
No, what I'm getting at here is how many of you chose to do this in an object-oriented manner.
I did object.
So, I'm going to create a class. And this class is going to be called,
Lookup table. Super strings.
no, I like lookup table. So we're going to create a class called lookup table. Now, lookup tables are going to hold several pieces of information. So, first of all, we need to know how many elements are in the table. So we're going to create a field called count. All right? This is where that ID 0, ID 1, ID 2, ID 3, where that stuff comes from. Make sense? Okay. Then we're going to have a linked list. I need to create another object. What object should I create, Joey?
Well, I wasn't paying attention, but what are we looking at here? Why do you need to create another object?
I'm asking you.
Okay, so
Lookup record symbol, okay? So we're gonna call this guy a table record because we're probably going to expand on that. If you remember when we read the little blurb in our book, initially, what are we keeping track of? We're keeping track of just the name of it, right? But eventually, we'll probably be keeping track of the type, might be keeping track of scope information, the value. Eventually, we probably want to have a value, right? Whether the value is stored inside the lookup table or whether the lookup table holds the pointer, the memory address where the value is held, whatever. It's very possible we're going to want to expand on this to hold more than just a token.
I agree.
So right now, we're going to create something called a table record. And a table record is going to have a private string, just call it name. All right, so we're going to have a public constructor. Shut up. If you always got every question right, then you could talk all you want, but you don't, because you don't pay attention when you're talking.
Get every question right now. Let's go.
Only if you even know what questions I ask. You're too busy babbling. All right, so this guy is going to take in string name as a parameter. I'm going to say this dot name is equal to name. All right, then we need to have the ability well, we'll add it when we need it, but we're probably going to want to have some way of getting the name of our table record out. Okay? So, back to our lookup table. Our lookup table is going to have a private linked list of table records. This guy is going to be called, here, we'll just call him symbol table. Okay, and we need to import java.util.linkList. Oh, and by the way, this is that object that you're not allowed to use in your 300 class. So you're about to see the punchline of what you're learning how to do in there right now. All right. So we're going to say public lookup table. We're going to start count off at 0. And we'll set symbol table equal to a new linked list of table records. So that'll initialize our symbol table. All right. Now we need to add the ability to add a symbol to our table. So add entry, if you will. Actually, let's call it add table record, since that's what we named our object. So we're going to have for right now, I'm going to make it return it. We'll make it return an int. So it's going to be public int add table record. This guy is going to take in a token as a parameter. And what's he going to do? He's going to add that symbol to the symbol table, which is this guy. Well, how do I do that? So I'm going to say symbol table dot add new table record token. Then I'll say count plus plus return count. So initially count will be 0, right? And our example shows that the very first identifier is a 1. Okay? It's 1 based instead of 0 based. So what will we do? We add the very first thing, what was our example? Position. We add position. Position will come in here as a token. We'll add it to our linked list by creating a brand new table record with that token. Then we'll increment count from 0 to 1. Then we'll return the 1. Make sense? Okay. So we'll go back to source reader. inside of our source reader, we need to create an instance of lookup table called symbol table. Actually, just for naming conventions, that actually threw me off here. We need to go back into lookup table, that object. I don't want to make the name of my linked list in here symbol table. I want to call it just the table. Because we might be using this object to create other lookup tables, not just symbol tables. Okay? So internally, we're going to use this guy as the table. Where we use the variable name symbol table will be out here inside of source reader when we create an instance of lookup table called symbol table. Okay, then as part of our constructor, we're going to say symbol table is equal to a new lookup table. And I don't think lookup table takes any parameters in their constructor. It just zeroes out count and establishes our linked list. I keep misspelling symbol. Okay, so there's symbol table. Make sense? Okay. So now, if we are not looking at a reserved word and we're not looking at a literal, we must be looking at a identifier. And what do we do with identifiers? We're going to return opening square bracket, or opening angle bracket, sorry, followed by the word ID, followed by a comma, space, just like this, right? Square bracket, ID, comma, right? Doesn't this say ID? Doesn't this say ID? Doesn't this say ID? It's hard-coded ID. We're gonna add the number. We're gonna add our number in, but right now it's just a generic identifier. All right. So now we've gotten that part, but now we need to get the number. Where do we get our number? We get our number by adding a table record to our lookup table, and that guy returns the number.
You gotta tell me something here.
So we're going to say this dot symbol table dot add table record token, and that guy will boil down to the integer that we want after it adds it. We'll concatenate onto that, this. Yeah.
Won't that add one more than whatever we just added it to? Because it doesn't return it until after it's added.
Correct, but we did that on purpose because this guy is one based. The very first symbol is the number 1. So the very first time we add something inside lookup table, count started off as 0. So we'll add it, make it 1, return the 1. The next time we'll add it, make it 2, return the 2. Make sense? All right. So this guy, Beaker, starts off with all the constant crap that comes before that integer. Concatenates onto that the actual integer, that's the result of our adding table record, and then finally puts our closing angle bracket. This is what our function for lexically analyzing a token should do. So now back here, after we read in a token, we want to say if cur token is not equal to null, we'll print out this dot lexically analyze cur token. Make sense? So when I run this, I get all my tokens. And actually, it seems like maybe in our, I don't think there's supposed to be a space after that comma. It looks a little weird to me. So we're gonna go back to our source reader where we're building that guy. Just take that space out. Now it's legit. Look at that. Okay, so that was your homework assignment. How many of you got it working, out of curiosity?
I think I was pretty good. I don't know if I think I might have did a 0 offset.
How many people tried to get it working but didn't get it working? How many people didn't even attempt the homework assignment? That wasn't full voter. What did you do?
Oh, I tried.
You did-
They give me very far.
What's up? You didn't vote. Okay. So, what's the next step? After we lexically analyze our code, we have to look at our syntax. Syntax what?
Don't worry.
Joey's drunk over there. Syntaxally and
So we have to look at our syntax analyzer. How is this going to work? Well, first of all, we need a tree data structure, don't we? Yet when we add stuff to our tree data structure, it needs to happen in a very specific way. So we need to figure out what's the right, do we use a built-in tree? Or do we write our own tree? What's something that you can say about this tree? So if you look at this example here, definitely rate heavy. Okay, that's true. So this is certainly not a balanced tree.
All the IDs on the left.
Also a true statement. All the IDs are on the left. Is this a binary tree? Sort of. Okay, why is it just sort of a binary tree?
It's not like an equal binary tree. Only does one thing. It's not sorted by definition.
Okay? Okay, so these things are usually called B trees. Okay, so this is a B tree. It doesn't follow that math thing of binary trees where it's everything that's less than the root node goes to the left, everything that's greater than the root node goes to the right. So I usually refer to these as B trees. It is a binary tree from the perspective that at most it has 2 children, correct? And in fact, you'll see that literally every root node has exactly 2 children. So at some point we're going to have to cross that bridge to determine if that's guaranteed to always be that way. Anybody have a gut feeling?
I feel like it's not going to stay that way. Because you can have more than one thing that is equal.
Operator just operates on one.
Yeah, it really depends on the language dictates what this tree is going to look like. Because you might have an operator that operates on one thing or operates on more than 2. Like plus plus. The plus plus operator operates on just one thing, right? Go ahead, Joey.
Alright, bro, this is from the lexical analyzer.
All right, bro, this is what. Let me throw this down.
Alright,
It's like, all right, go ahead.
so
Throw it down, Joey.
give me a beat.
Like, if you have more than one identifier, right, that's got the same name, does it appear in the lookup table once? Or, like, if it's different based on the scope or something?
Yeah, see, I purposely omitted that because at some point we're going to have to circle back and talk about scope. For right now, if you had one identifier, if we assume we're only working with one scope here, if you added position more than one time, it should detect that position was an existing identifier and return it. So if you want to go back and do that, let's just for completeness. Okay. So for completeness, let me just give you the example. Vine. Okay, so we have this guy. So let's say later on we add a force equals mass times acceleration plus position. Okay? Now we're going to see that last time, so when I run this one more time, we're going to see that final position is ID 11 when it really should be ID 1. That make sense? So before we just haphazardly add something to our lookup table right here, before we just add it, we need to see if it's already there. Make sense? Well, we have something called a table record, and right now we're checking our table record by name. So what I'm going to do is I'm going to create a public method inside of table record. It's going to return a Boolean called matches. Yeah, we'll just call it matches. No. We call it has name. And this guy will return name dot equals name. But we need to say this dot. Well, for one of them, we need to say this dot. All right, so this function inside of table record gives us the ability to pass a table record a piece of information. Well, ask a table record, is this name the same as another name? Make sense? So what we're going to do here is we're going to go back to our lookup table, and before we just haphazardly add something to our table record, we're going to go through and we're going to say for int I is equal to, actually I'm going to do it this way. Int pos is equal to 1 for table record tr in the table if tr dot has name token, I'm just going to return pos. Otherwise, I'll increment pos. Now, if I get through this entire minefield without returning a position, that means it's not there. And I'll go and just do what I did before. Add it, increment count, return count. That make sense? So what I'm doing in this case is I'm checking to see if token is already in the table. And return its one based position if it is. That's why I started pos off at 1. Okay? Yeah, but unfortunately, 3/4 of your brains don't document themselves. I'm talking about you, Beaker. Oh, go ahead.
So like it's say if position is in that twice, you'll just find the location where it is.
Yeah, right. It'll find the location where it is, but not try to add it again. Because, I mean, even though this is just outside the for loop, I would never get to here if I hit this line. return makes the method immediately end. Okay, makes sense what this code's doing? So now if I run this again without changing anything else, we'll see that that final ID will be ID 1. Okay, so we have our ID 1. Go ahead.
In that other, in the table record method, what did the has name do?
Has name takes in a name and checks to see if this particular table record has the same name as the name you passed in. So it's our little built-in function to say, yo, does this guy already exist? Are you the same as the guy I'm about to try to add? All right, this makes sense? All right, so are we happy with this now, Joey? This is complete?
Good enough.
All right, so
Do any syntactical analyzing.
our next step is to go from this stream of tokens, which we've created, right? Is to go from that to syntax analyzer. That is, create this tree. So let's look at syntax analysis a little bit. So, second phase of the compiler is syntax analysis, or sometimes it's called parsing. And now we're breaking apart our tokens into individual pieces. Parser uses the first components of the token produced by the lexical analyzer to create a tree-like intermediate representation that depicts the grammatical structure of the token stream. Have we produced a token stream? As of right now, we have a token stream. We're printing it out to the screen, but could we have just as easily added that to a linked list or something? So we could have a linked list of tokens right now that have been properly lexically analyzed. Okay? A typical representation is a syntax tree in which each interior node represents an operation. Okay? And the children of the node represent the arguments of the operation. Now, we're going to keep a very simplified concept of this right now. We're not going to worry about the existence of operators that operate on less than one thing or more than two things. In our simple little language right now, all operators operate on two things. You have a left operand, you have a right operand. Make sense? Position plus sum. That's what they all look like. That's why our tree in this example always is a B tree. Always has an operator at the top level and a left and right to that. Okay? So this tree, the one they've shown us up above, shows the order in which the operations appear in the assignment are to be performed. The tree has an interior node labeled asterisk with ID 3 as its left child and the integer 60 as its right child. So let's go and look at that. Here's the asterisk. ID 3 is the left child. 60 is the right child. What will this boil down to? If we were executing this code, what will this far right subtree boil down to? An integer. Good. This is going to boil down to some integer. And we'll then use that integer as the right operand to this operation, which will boil down to an integer. Then we'll use that integer as the right operand of this operation, which will boil down to an integer. Oh, actually, yeah. To this one, it will boil down to an integer, and then equals says to assign that integer here. Yeah, this is the assignment operator. So the integer that this boils down to will be the same integer that this boils down to, except it'll store the value here. And that's a true statement even in Java. If I did system.out, let's say I have an integer named A, and I say system.out.println A equals 7. It'll print out the 7. The 7, it'll boil down to a 7. But A has been assigned the value 7 as well. Okay, so this operation right here will boil down to an integer. Okay? Okay, so this paragraph here is just talking about what we just did. This is almost like a recursion tree, except there's no recursion. These guys have to wait. This guy can't happen until, this guy can't do its operation until this guy's returned. This guy can't do his operation until this guy's returned. So on and so forth. The subsequent phases of the compiler use the grammatical structure to help analyze the source program and generate the target program. So when we get to chapter 4, we're going to be looking at context-free grammars that will specify the grammatical structure of the programming language. That's kind of like what we did last semester in the programming language class. We had those grammars that described our languages, right? So now we're going to have to use grammars to help us check syntax of our languages. That's a whole nother level of things we didn't deal with last year. Last semester, well, it was both. When we created an interpreter, we never worried about syntax. We just always assumed that the syntax that was passed in was accurate, correct? One of the jobs of a compiler is to give us feedback as to syntax errors, correct? When we run our Java program, when we hit that play button, we're looking for either output or error messages, correct? So one of the jobs that we hold a compiler to is syntax checking. An interpreter, not so much. Many interpreters have that. They'll give you some sort of error message, but it's not really a requirement of an interpreter. Okay, so to create this tree, we're going to have to create our own. What I'm going to suggest we do is create our own tree object, so that when we add stuff to the tree, it automatically puts it in the right place, rather than try to repurpose the generic tree data structure from Java. That make sense? So what we'll do is we'll come back next time. We're going to create our own object. We'll come up with a clever name for it. That every single, we won't actually build our tree until after we have finished our lexical analyzer. So we'll probably feed all of our tokens, all of our lexically analyzed tokens into a linked list. Then we'll go through that and add them to our syntax analyzer, to our tree, hopefully producing something like this. Make sense? All right, so no assignment. We'll come back on Friday. We'll write part of this. Then I'll give it to you as homework. Go ahead.
Kind of a weird question. So right now we're writing a compiler in a programming language that then gets compiled.
Yep.
So kind of like a chicken before the egg kind of situation. But they have to write like the first compiler like in assembly.
Yep.
I guess we're not doing that.
Yet.
Oh no.
What did they write the first assembler in?
No, right. No, it's a really interesting question. Yeah. At some point, somebody had to write the first something, right? That actually connected those one-to-one dots.
That must have been a crappy job.